Hi, my name is Savannah Quistad. I am remaking this section of the video where I taught. I partner taught my lesson with one of my peers, Trinity Archer, and I'm now filling in the sections that she taught in the original lesson. So this video will be a mashup of lessons that I'm teaching here and also lessons that I actually did in front of a live audience. I'm just going to be filling in the gaps with some of the things that she did to kind of show my breadth of knowledge. So this will be the start of the video.
Just make up a way that you think makes sense. Okay, we got one. Can I? Is there a way to? I can't reach that at all. There's no way I'm gonna be able to reach that. No. I think I'm tall enough for that.
That's the way right there.
Thanks, Callum. Appreciate you. Thank you guys. Yeah, that's what I'm saying. That's what I'm saying. 2, 3, 4, 5. Thank you, Mina. 6, 7. 8. Okay, we're going through it. Okay, would anybody like to maybe volunteer an idea they had or what they thought to do? Yes, Finn.
Okay, so I think we did this in like Algebra 2.
We did do this in Algebra 2.
No way.
Yeah.
So is it just like 2 and 8 and then it's a 10?
100%.
3 and a 7 and it's a 4. And you basically just make the same size matrix except you add like each.
Yes, 100%. Okay, guys, so basically, we're going to start with matrix addition and subtraction. You just add each element, but it's very important that they are the same dimensions. You cannot add matrices that are of different dimensions. So, Finn, what did you get?
10 and then 4.
Oh.
Well, 4 is in the next one, yeah. And then 6 and then 7.
Thank you, Finn.
Yeah.
Much appreciated. So that is our warm-up. Thank you, guys. All right. Can I start? I want to start over here. We're going to move over here because I want to give it a title. Okay, fellas. I'm going to erase all of this. Can I erase all of this? Is that okay? Oh. Okay, so we're gonna do a little bit of, this is not a very good pen, can I use? Writing over that. Matrix. Review. Or maybe it's not review. All right. So first, would you guys like to write down the definitions for addition and subtraction, or do you think you have the idea? You guys all got the idea? Okay, awesome. We'll move on to first matrix notation. So for matrix, which plural is matrices, fun fact. Matrices are of m times n dimensions. Where m is M is horizontal rows. And N is vertical column. So when you have matrix notation, elements, we'll do this, elements are represented as, sometimes they're just, you have the notation where it could be a number, or it's usually like a letter. This doesn't necessarily have to be A, sometimes it's X, but it's A, and then it has subscript A, or I, J. So I represents the row, and then J represents the column. So if I were to write out an example of this, you would have A, 1, 1. Sometimes you'll see notation and you'll think, oh, does that mean 11? No, it does not mean 11. It means 1, 1. So that means row 1, column 1. And then you'd continue by going A, 1, 2, because it's still row 1, column 2. A, 1, 3, and then so on and so forth. So this would be A, 2, 1, A, 2, 2, A, 2, 3, A, 3, 1, A, 3, 2. Can you guys see this? Okay. A, 3, 3. Okay. Can everybody see it? Yes, Laura.
Like, if the matrix were like really big, how would you distinguish like which part is the I and which part is the J?
Do you mean like?
Like if it was like 112, if it was like 11, 2, or like 1 and 12.
That's a really good question. And I'm going to be honest, none of the examples like you'll ever see of this notation usually don't get that big, because if you're dealing with a matrix that's like, I don't know, bigger than a single digit number, I don't know, it just is not very common from what I've seen. But
Okay, so I don't know fully, but if you look at the other numbers that are around it, you should be able to like guess what it is, because
that's a good point.
you know, like the
Yeah, because you got like 1, 1, 1, 2 for the second number, 2, 2, 2, 3, 3, 3. But anyways, that is just some general notation. I don't know, does that like answer your question? I don't know.
Question about if you have double-digit rows or.
Yeah, I don't know. Would you do like a comma?
I would guess a comma.
Maybe probably a comma. I don't know. They don't really have any examples of it in the textbook, so.
Yeah, sometimes they'll say A sub ij, and then they'll just say I equals 11, j equals 13, maybe.
Yeah. Okay, awesome. And then, okay. Another question. We can define what this is more like definitions, what a zero matrix is. So, any matrix where each of the elements are just 0 is going to be equal to 0, which, is pretty self-explanatory. You can write that down, but just so we can like establish that it is equal to 0. Okay, so now, can I erase all this? Is that fine? Let me see. Can I erase all this? I don't know. Yeah, I'll move on over here. Okay, now we are going, actually there's one more thing we're going to define over here. I almost forgot about that. We are going to define what a transpose matrix is. Transpose matrices. Okay, so whenever you see a matrix, they are going to be denoted, Isla and Heather already kind of talked about this, they're going to be denoted by a bold capital letter in the textbook, but when we're writing it out, we just write it out as a capital letter. So I will define matrix A as So whenever we transpose a matrix, we're basically just flipping the columns and rows. Usually the textbook will do this just to save space. I don't think it's like very common in like for like a practical reason, for at least what our chapter does, and it's going to be denoted by AT. 2, 4, 1. With a T at the top. So sometimes, especially when you see vector matrices, which again Heather and Isla kind of defined, if they can be columns or rows, and sometimes they will just be denoted with a T at the top to show like, wow, this was a column vector, but we made it a row vector.
For Campus High School. Lock your doors. Students, remain quiet and follow teacher directions. This is a lockdown for Campus High School. Lock your doors. Students, remain quiet and follow teacher directions. This is a lockdown for Campus High School. Lock your doors. Students, remain quiet and follow employees and the entire campus to ensure that is the case. Please remain calm as always, and we will get you more info as soon as possible. Thank you.
Don't do that.
Okay, guys. Yes, Callum. What? I can't hear you.
Good morning again, Campus High School. Thank you for all your efforts during that lockdown. We believe it was a maintenance issue and we are investigating still. We have checked the campus multiple times to make sure we are clear. Have a great Friday.
Yes. Yes. Yeah, it's not supposed to. It's not supposed to be there. Okay, guys. Okay, guys. Quick correction. I put a T up here. It is not supposed to be here, actually. I forgot about that. It's just, this is transpose, which is equal to this. Yes. Forgot about that. That's not there. Sorry, guys. My bad. Okay. Awesome. Okay. And then next definition, which Trinity's going to get more into this, but I'm just going to write it down for the sake of completion. So vectors, which we kind of also already covered. I'm just writing they can be column or row. So it can be one or the other, as long as there's just one column or one row. Okay. Then we will move on to, we'll do one more, actually. Okay. We will move on to matrix multiplication. So this one you may or may not remember. Okay. Okay, so matrix multiplication. First, we will talk about distribution. Okay, so when we will take our matrix, well, I'll also call this one A. 1. You can multiply both sides, or like the whole matrix, by like one constant value. So I could go 6A equals 12, negative 24, 18, 6. So doesn't matter the size or dimension, you can distribute this over the full matrix. Okay, then next we will get to just regular multiplication. So when you have two matrices, you can multiply them by like what is called like their dot product. We kind of already talked about this, but to make it simpler, you can multiply matrices that have different dimensions as long as the number of columns for the first, or for the number of rows for the first one, or the number of columns, which is like the amount of terms in the first row, equals the number of terms in the first column. So how this is like an easier way to do it is I will write out the dimensions under the matrix. So that's a 2 by 2, and this is a 2 by 1. So whenever you're writing the dimensions, you go the front. You've got your number of rows times number of columns, which kind of comes into your n times n thing. And then if the two middle terms match, then means you can multiply them by each other. And then these outside terms, you may remember this, that's going to be the dimensions of your new, you can say, dimensions. That's going to be the dimensions of the new matrix you create once you multiply them. So I'm now going to multiply this out by first going this by this. Multiply those, and add them together. Does anybody want to tell me what your like first term would be? If anybody would like remember this process? -8. Yes, -8. And then what the next one would be down here. 18. Yeah. Okay. Does this process make sense? Because if you have questions about it, please let it be known. Because this is like essential for all like matrix stuff in the future. Do you guys want another example of this, or does that make sense? Is everybody general consensus? Okay, cool. And then we will do some notes about, so matrix multiplication. This is very important, is that matrix multiplication is not commutative. So there's two things that it is though, so we'll write down a note. Matrix. Matrix multiplication is associative and distributive, which I'll write down like an example of that, but it is not commutative. So is associative and not. Okay, so to kind of give an example, again, matrices are represented by capital letters. So you could have A times matrix B times matrix C, which equals matrix A times B, then times C. This would be equivalent because of the order that they're in, because they're one after the other. But if you were to do A, B, that is not equal to B times A. Remember, and these represent matrices. And then finally, matrices are distributive, so okay. And then the last, I don't know if I have enough room for this. The last property is that if you were to have, here, I'll kind of, matrix A times matrix B, that equals 0. That doesn't necessarily mean that matrix A and matrix B are equal to 0. So each of them could both not be equal to 0 and still equal 0 when they're multiplied. Okay, I was gonna do an example for that, but I don't know. Does that make like sense? Like, you could think of an example for this. Like if you did like 1, 1, 1, 1, and then you had 1, 1, negative 1, negative 1 multiplied by each other, they would all cancel out and just equal the 0 matrix, even though both matrices are not equal to 0. Okay,